hang on. Okay, now you should be able to hear me. Hello, Alex. Can you hear me? Oh, I'm going to mute you. I'm going to mute everybody again. Great. Thank you, guys. I appreciate the feedback. So, Alex, you were interested in showing us something. What was it? I'm looking at the chat box. Yeah, can you guys see the chat box back there? Okay, you should all be able to hear now. Just you make sure your speakers are turned on. Well, let me give you an idea of what we're gonna be doing tonight. I'm on Blackboard. I'm in this sessions section, of course. I'll just reload that, and I'm looking at session 5. We're going to start out with a little bit of an exercise we're going to do together. It's going to demonstrate functionally what the central limit theorem is. How many of you guys know what the central limit theorem is? Heard of it before? Somewhere in the deep, dark recesses from undergraduate, you might have heard of it, right? CLT, so the letters CLT together someplace, right? So, well, then we're going to learn something tonight. We're going to learn something new tonight. We're going to learn about central limit theorem. It's going to involve an exercise that we're going to do together to start off things. Then I'm going to do a few things that'll demonstrate how it works and so on and so forth, how we apply it. When we get done with that, I'm going to go into this folder for session 5. There's a bunch of documents in here. First of all, there's a textbook readings. You can always do that afterwards. There's an exercise. There's some files here we're going to be going through, including this Word document, which is the exercise that we're going to be trying out. I also put some videos from some previous times we've done that, previous semesters, just so you have a second look at this in case you want to get to it before I post the recordings of tonight's session, or you can just wait for the recording of tonight's session. When we get done with that, I figure it's going to take about an hour. I'm not sure exactly how long because it's going to be fluid. There'll be questions that come up and stuff like that. When we get done with that, I've also posted links to 4 videos that are lectures from previous semesters that I've done with Levi. And the lectures cover this same material from more of an academic perspective. They're PowerPoints. PowerPoint slides are on there also. They're PowerPoints. They add up to a total of about 35 minutes or so. I think the first one, I think, is the longest. It might be 15 minutes or something like that. But we're going to take a break from the online session. And here we're going to play those. And after each one, we're going to post more and we'll go over it and we'll discuss it a little bit, see if there's any questions. So you guys that are at home, you can log off of the online segment of this and you can look at these 4 sections, these 4 videos that cover this material in sequence. And then we're going to come back again. So as far as exactly what time we're going to come back again, if you go back to the top to the folder for this session, I gave you a second link down here. If you use that second link, that's where we'll be when we come back. Okay, so you guys at home can watch those videos on your own, and then we can all sync up afterwards again to kind of just sum up everything that we've learned together. So for right now, I'm going to get started on the exercise. If you want, might want to open that Word document that's on Blackboard. That's on session 5. I'm going to minimize this because I actually have it on my desktop as well. Here we go. Good. Let me move this out here. And let me make sure I'm recording. And I am recording. Oh, okay. I got a few people online that have heard of it before. Good. We're going to work with I gave you a table here. This is just a version of it that's an image. There's another version of it that's an Excel file. And this Excel file represents a population, right? These numbers might represent blood pressures, they might represent some other kind of measurement. But the important thing about it is that they were generated using something that will give us approximately a normal distribution for these numbers. But they're assembled here in a random manner, right? So if I wanted to know from this population, a population of 100 people, most of the population is going to be dealing with a much bigger population in the United States, population of all the diabetics, population of graduate students in the CUNY University system. You know, that might be, I don't know, might be 10,000 or 20,000 or something like that. So in a situation like where you have a big population like that, it would be very difficult, very costly to go around and measure everybody, test everybody, get a measurement for everybody, collect information from everybody. So very often, in order to get an idea of what the average for a measurement is for a population, what the variability in that population is like, we'll take a sample. Well, we're going to simulate that right now, the idea of taking a sample from a random sample from a population. Random is very important because if we take a biased sample, we won't really know what the whole population looks like. So we're going to simulate that, except our population is going to be 100. You can make believe it's really 100,000 or a million or 100 million or something like that. You can make believe, but it's as if this is our population and we can't afford to take a measurement for all of them, but these are really the background measurements that are actually there. So unlike the situation that we would be in normally, we could, if we wanted to, actually calculate the mean for this entire population. Okay, so the mean for this entire population is 50. Actually, you want to know something? I'll bet you it's not exactly 50, because I'll bet you, there you go. If I spread it out a little bit, you can see it's a little different than 50. I can also calculate the standard deviation, sigma, for the entire population. Okay, and it's going to be equal to standard deviation, parentheses, and let's see what the standard deviation for the whole population is. So it looks like the average for this population is 50, and the standard deviation for this population is 9. Now, in our imaginary world, we don't have the resources to actually measure everybody. So this we don't really know. We just are using this to understand the relationship between the sample and the actual population. So normally we would not know these numbers. Okay, so what would we do in this case? What we would do is we would take a random sample of a smaller number of subjects from this population, and we would calculate the mean and the standard deviation for that sample. And we would hope that the mean of that sample and the standard deviation of that sample would echo or mimic the same measurements for the entire population. There would be a good estimate of it. Obviously, what would make a better estimate? What's a good way to get a better estimate? Bigger sample size, right, would be a better estimate, right? So sample size is going to be important to us. So we're going to be interested in what that sample size is, particularly in this case. Okay, so I'm going to open up that document. Where is it? There it is. Okay. So my first problem is, how do I get a random sample from this group of people that I have? Okay, and the way that we're going to do it in this case, there's a number of ways to do it. There are computer programs that you can use to randomize social security numbers, to randomize phone numbers, to so on and so forth. But old school way of doing this is there were books that were published that have tables in them. Here's one, for instance. This is a random number table. These tables were generated by the software or some other mechanism, and they're single-digit numbers organized into groups of 5 that have been produced in a random manner. So you could literally stop anywhere, just put your finger, like in a phone book, just drop your finger in somewhere randomly and start from that point. I'm going to pick right here, 40. So I'm going to take a 2-digit number. I'm going to take these in blocks of 2-digit numbers, 40, 27, 30, 94, 26, and so on and so forth. I'm just going to go across from the point where I started. I'm going to go across randomly. Presumably, these are random numbers, right? That's why this jet table was generated. This random number table was generated. Except what I'm going to do is I'm going to use these random numbers to help me select the subjects that are going to be my random sample for my population. So I'm going to use the first number. Notice two numbers, right? 4 and 0. I'm going to use that to represent the row and column number from my population. Okay, so if I come up with 40, that's going to represent the person that is in row 4, column 0. So that's going to be 65, right? And the next person is going to be 27, row 2, column 7. Row 2, column 7 happens to be 39. Okay, so what I'm going to do is I'm going to ask you guys to do your own random selection. And I'm going to say, let's make our sample size equal to 9. Okay, should we do 9 or 16? 16. Let's make our sample size equal to 16. So everybody, you guys online do this also. We're all going to create a sample from this population of 16 numbers. And then we're going to take those 16 numbers that each of us calculates different. Don't start from the same point I did. Pick out your own random starting point. We're going to take those 16 numbers, and you're going to find the average for your sample, right? And then we're going to work from there. Okay, so you don't have to calculate standard deviation. You can if you want to. But what we want is, number one, we want the average of those 16 random numbers that you've selected. Okay, so it's going to take us about 10 minutes to do that probably. Now, if you want, you can do standard deviation also. We're not going to use, for the next step, we're not going to use your standard deviations. But your expectation is that you don't know what these two numbers are. You don't have any idea what those two numbers are. So your only information about this population is how close your sample mean and standard deviation comes to the real population mean and standard deviation. So you might want to take a look at that. That's a little bit different than what we're going to be doing with central limit theorem, but it might be of some interest to you to see how close you wind up getting to those numbers. Okay, so I'm going to do it also. And as we get done, you guys can either post, you guys online, or even here if you want, you can either post onto onto the chat box what your average was for your 16 numbers. Or if you're here, you can just, when we get to the point, you can just yell them out at me. So I'm going to go back to where I was, 40. I'm going to need to make a little bit more room here. I'm going to make this smaller for starters, at least until I get to the point where I can do my calculation. I'm sorry? You can't use Excel? No. With the licenses? No good? You want to switch machines?
Oh, no, actually.
Oh, okay. Yeah, sometimes they're a little slow. Okay, 40, 27.
So we don't use that table. We just use this table.
What's that?
We just pick numbers from this table, not the book table.
You're going to use this table to get what numbers you're going to use, the row and column. But then you're going to go over here to the Excel file, and you're going to go, for instance, the next one I'm looking up is 27, is row 2 and column 7. So my next number is 39. So you're probably going to want to type them into Excel, maybe below the box like I'm doing them here, so you can do your calculations. Okay, so 27, 30, 52. 94. Two. 62. Okay. 40. $15.73. Let's see what they got here. 2, 4, 6, 8, 10, 8, 6, 4. First digit's the row, second digit is column. You can actually do it the other way around if you want, right? Because it's random. Doesn't matter which way you do it, really, as long as you're consistent. You don't do anything to favor one way or the other. 82, 27. Oops, the wrong one here. Okay, 6 and 32. Okay, take out 16. What's that? Oh, yeah, oh, you're using my version of it. Oh, you mean this one?
No, the other one. The one from the book. Well, both of you combine them.
Okay, hang on. I'll tell you what, I'm almost done with mine. Let me just finish mine up. Okay, I'm going to get my average here. That's 16, right? 2, 4, 6, 8, 10, 12, 14, 16. Yep. So the average is equal to all of these. Oops, I should get this out of the way here. It's not going to work there. Average. Oops. Ah. You lost count. Okay, I got an average of 52.5. I'm off a little bit.
No, you have a little, I got 53.
There you go.
49.
You got 49. See, some of us are higher, some of us are lower. That's just what you would expect from a random sample, right? Repeated random. Oh, look how close my standard deviation was, though. I'm gonna bring this up to the front so that if you guys want, you can use it to. 7.
Mm-hmm.
Wow. Okay, that's a little bit off, right? I'll leave that up front there for anybody who wants to use it for a few moments. I'm going to give the guys online a chance to do their calculations. Oh, I'm starting to see some averages show up. Okay.
Reduce that size. What does it do?
What?
Reduce the size. Because my number is the random sample, and mine is all the way at the bottom.
Oh, okay. How's that? Is that good?
And then I need to see the other one.
Which one?
One?
Oh,
So
God. That's kind of hard for me to do on this little screen.
Never mind, it's okay.
You can, if you want, you can pick up from another spot.
Yeah.
Okay, oh yeah, I'll bring this over. I'll put this over on top here. Or you don't have to go across. You can always go, straight down straight down one of these columns. I'm going to give you guys another 4 minutes or so, and then I'm going to start collecting results. Okay, so now, what I'm going to do now is I'm going to take all of the sample means that everyone collected. Everyone that took a sample size 16 and got an average. I'm going to create a new distribution, which is going to be only the means of size sample 16, of the averages of the means or averages of samples of size 16 from this population. And we're going to see how this distribution of those sample means differs from the distribution of the actual values from the population. I'm going to move this over just a little bit so you can see. Sample size is 16. Okay, I'm going to start writing in here the averages for that I'm getting from the people at home.
You have the green arrow. That might be
What's that? On there, there's a green arrow.
no, in the corner. You know when they done the green arrow at the green little thing on the corner of your calculation? You should have 52.2. See, is that like a calculation arrow?
Oh, that thing?
Yeah.
Let's see. Formula refers to empty cells. It's just warning me that when I did the calculation, I included all of these cells. However, by default, Excel doesn't count empty cells when it does an average. So it actually did the average correctly. But it was just a warning. Okay, let me start writing these numbers now for the guys at home. Or did I mess up the first number? Okay, let's see. Okay, let's start from there. Sophia caught me making a mistake. That's okay. Let's see, 40s. I'm gonna round these. I'm gonna round these rather than just to make it a little bit simpler. 6. Oh, that's my that. Get rid of that. Whoops. I know my God. Now you know I'm having for dinner.
We're that fast.
Yeah.
Don't worry. Oh, I think
Salad, yeah. Salad. 52. Okay. 53. 51. 49. 53. 47. Oh. 47. Okay. Thanks for the standard deviation, but I'm not going to use it for this particular thing. 49. And okay. All right. So how about you guys here? What numbers you get? 52? Okay. You can round it off. What's that?
49.
Okay. 49.
53.
53. Good. Any others? Yeah.
I got 55.
55? Okay. I'm sorry? That's okay. That's okay. This is enough, I think, for us right now. Okay? So I'm going to take these numbers. Now these numbers are these numbers are averages of these numbers are the results of taking an average of a sample of size 16 from this population. So the first thing I'm going to do is I'm going to find the average of all the averages. Parentheses, and take the average, and as I would expect, it's pretty close to 50, right? Because our expectation is now imagine that I had taken an infinite number of samples from this population. Then my average would definitely be the same as the population itself. The more samples I take of that size, the closer I'm going to be to the real population mean. So we can say that the mean of the sample averages approximates the mean of the population. But let's look at what happens when I want to calculate the standard deviation for these sample means. Right? This is the standard deviation for the means of size 16. Okay, so let's see, standard deviation, parentheses, and I'm going to pick all these numbers out. Okay, standard deviation is equal to 3. What was the original standard deviation? It was 9. What's the relationship between 9 and 3? Right, it's 3 times. Besides, well, think of it another way. Rather than 3 times, it's also the square root. Right? So we've just discovered, I can't believe it came out, and it never comes out this well. Right? We've just discovered that if we take repeated samples from a population, right, our mean will approximate the population mean, right? But if we take many, many repeated samples, the variability of those sample means is going to be smaller than the variability of population. In other words, the smallest number here, minimum, the smallest number here is 27. The biggest number here is 69. That's how spread out these numbers are in this population. But when I take sample means, they're much tighter. The results are much closer together when I take sample means, aren't they? Right? So what does that tell me? That tells me that the sample size impacts the variability of repeated samples. Well, what's so good about that? What's so good about that is that if I take a population and I'm about to go and I'm going to take a sample from that population, I have an understanding about how samples are going to behave based on the sample size of that population. So I'm gonna go back to our little table there, a little document, a Word document. I'm gonna get this out of the way. So to turn this into something that we can actually use, I'm going to go back to our understanding of the normal distribution. Let me blow this up a bit. Okay, and I'm going to bring up a notebook page. Okay, hopefully this will be blank. Okay. So what we just demonstrated here was that if the mean is equal to 50 and the standard deviation of the population is equal to 9, we found that the mean of the average mean of samples that we might take is going to approximate 50. If we take a sample of size, and if we take a sample of size 16, right? Well, we would expect that the standard deviation of our samples is going to be equal to the standard deviation of the population divided by the square root of our sample size. Okay. So actually, tell you the truth, it didn't come out exactly. The three became pretty close. So that would be 9/4, right? So we would expect it to be about a little bit bigger, somewhere between 2 and 3, let's say, right? So our sample size impacts what our standard deviation of repeated samples from the same population are going to be. So if we took a sample size of 25, we would expect the standard deviation of repeated samples to be standard deviation of the population divided by the square root of the sample size 25, 9/5, right? A little under 2, right? So the bigger the sample size is, the narrower is going to be our distribution of possible sample outcomes if we sample it over and over and over again. Well, why is this so important? The reason why this is so important is because the sample distribution that we got, the original population had a normal distribution, might have looked something like this. This distribution of our new of our samples now is going to be narrower, but it's going to have the same mean, right? But they're both going to be normal distributions. And when we're dealing with normal distributions, we know that 95% of the outcomes for the population is between 2 standard deviations below the mean and 2 standard deviations above the mean. Similarly, for our sample distribution, we're going to have 2 standard deviations below the mean, 2 above the mean. That's going to represent 95% of the expected outcomes when we do this process of taking a sample, right? So that's because we know our standard deviation for this. We use the term standard deviation so frequently here. When we talk about a distribution of sample means, right? The repeatedly taking samples and finding the averages for those samples. Instead of calling it standard deviation, we're going to give it a new name. We're going to call it the standard error. It's really the standard deviation for repeated samples from the same population. Okay, that's going to be called the standard error from now on. The good thing about that is that I know that I will expect that if I knew the population mean and standard deviation, usually don't, but if I did, I would expect that 95% of the time that if I took a sample of size 16, I would expect 95% of the time, because it's 2 standard deviations apart, that my result of taking a sample of that size from this population would result in an average of 50 plus or minus 2 standard deviations, right? So what do we say the standard error was? The standard error was 9/16 divided by, that turns out to be 4. That's 2 1/4, 2.25, right? Right. So it's going to be 50 plus or minus 2 times 2.25, or in other words, 50 plus or minus 4.5. So I would expect 95% of the time that I would get a result that's between 46.5 and 54.5. That's 95% of the time. If I were to do this with a true normal population, that's the outcome I would expect for taking a sample of size 16 and finding the average of those 16 individual values. So that's really nice. Does it mean it happens all the time? No, occasionally we're going to find a value, we're going to get a value less than 46.5 or more than 54.5. Did we get any here? Let's go back and take a look. Let me find that. Let's see if we got here. Did we get any that were 47 is the closest? No, we didn't even get it. We didn't do 20 samples. If we had done 20 samples, we would expect one of them likely would be outside of that range that we would expect our results to be in. Okay, everybody comfortable with that? What we did here, like just the idea that we're taking samples from this population over and over and over again, finding the mean and trying to understand what range of numbers we would expect that mean to be within in order to satisfy our understanding of the standard deviation and the standard error.
95%, if you took random samples over and over.
Random sampling over and over.
The 95% of the time we'll get
a value between 46.5 and 54.5. You guys tell me 95% of the time, what would be our range that we would expect it to be in if the sample size were 25?
so it would be
Yeah, let's see. Okay, so it would be 50. It would be 50 plus or minus this 2, right? 2 standard deviations on both sides. Now, the difference is the standard error now is 9 over 5 would be 1.75, right? So this 2 times 1.75. It's 9 over 5, right? In other words, the standard deviation of the population we know is 9, divided by the square root of the sample size, 25. So square root of 25 is 5. So 9 divided by 5 is 1.75, right? I am right there. Or 1.8, right?
always 2 standard deviations.
Yeah, because it's 95% of the outcomes are within 2 standard deviations. It's for 95%. It's going to be 2 standard deviations. If I wanted to see what range 99% of the outcomes might be, I wouldn't use 2. I would use 3 standard deviations, right? Roughly 3 standard deviations. Okay, 99.7. Right? Remember the empirical formula when we learned about that 1 standard deviation is 68%, 2 standard deviations on either side is 95, and this is 99.7 for 3 standard deviations, almost all the values, in other words. Okay, so I would expect that's 1.8 rather. 9 over 5 is 1.8. So 2 times 1.8 is 3.6. So 50 minus 3.6 is 47.4 and 53.6. I would expect 95% of the time. The only thing I changed was the sample size. The same population. Only thing I changed was the sample size. So our range of expected values is going to be a little bit narrower because of the greater sample size. Now, if I took 20 samples like this, how many times would you expect out of those 20 samples I would be outside of 46.5 to 54.5? Right? It's 95% certain. It's 95% likely that they would be within those 2 numbers. That means 5% of the time it's going to be outside those numbers. So 5% is 1 out of 20, right? Same thing as 20 is 1. Same thing as 1 out of 20. So you would expect at least that one time out of 20, if you did this 20 times, you would get a value that's either below 46.5 or greater than 54.5. Okay. And this again is a function of the sample size. What the sample size is doing to compress the range of numbers that we're going to get, because every time we take a sample of size 16 or 25 or 100, the larger the sample is, the closer that the result is going to be to the mean. So that means if we're looking at repeated samples, they're all going to be closer to the mean, right? Because of that increased sample size. Okay, so let's put this to work. And to put it to work, we're going to step back a little bit to remind ourselves of how we evaluate like populations and normal distributions and so on and so forth. If the total cholesterol values for a certain population are normally distributed with a mean of 200 and a standard deviation of 20, what's the probability that an individual picked at random from this population would have a cholesterol between 180 and 220? So I'm going to sketch that out. Okay, now remember, in this case, we're dealing with a population. The mean is 200, and the standard deviation is equal to 20. The question was, what percentage of the population would you expect to be between 180 and 220? Okay, so how many standard deviations below 200 is 180? 1. How many above? 1. So what area would we expect in here? Guys remember? 68,
68%,
right? 68% roughly, right? Okay, so that's pretty simple, right? 68% of the population. How about between 160 and 240?
That would be 95%.
Yeah, there you go. Right? 95%. Guys online getting that? Yep, I see a couple of answers there. Okay, that'd be 95%. How about between 225, how about greater than 225 milligrams? Okay, greater than 225 would be this area in here. Well, how are we going to determine that? Yeah, we got to go to the Z table, right? Because it's not an even number. Okay, so I'm going to go to the Z table. I have it. I think I have it handy in that folder that I have here. Okay, here's the Z table. And I'm going to go to, well, first of all, number one, what's the Z score? The Z score is going to be 225 divide, oops, that should have been 20 up there. Okay, 20, right? The Z score is going to be equal to the value I'm interested in, 225x, minus the mean over the standard deviation, 20. X minus mu over sigma. Okay, so that's going to be equal to 225. It's going to be equal to 25 over 20. It's going to be equal to 1.25, 1 and a quarter. My Z score is plus 1.25. So I'm going to go to my Z table, and I'm going to look up the Z score for plus 1.25. And we notice that the Z score, it's going to give you the area from the Z score to the left, right? So the Z score is 1.25, 1.2, and I got to go across 0, 1, 2, 3, 4, 5. So we're talking about an area of 89.44. Okay, but that's the area to the left, right? That's this area is 89.44, 0.8944 if you're dealing with probability. If you want to describe it as a percentage, you could say 89.44%. Right, so it's 0.8944. So what does that leave for the percentage of people that probability of selecting someone that's greater than 225, or the percentage of people? It's going to be 1 minus that, right? 0.8944. Okay, which is going to be equal to 0.1064, 66. Sound right? 56. Right? I think that's right. Right, about 10.5%. Okay, so that's going to be our probability. So let's go back and look at the next question they might ask about this. Okay, what's the probability of a person randomly selected from this population having a cholesterol of less than 150? Remember, this population, we're not dealing with samples here. We're going to come back to samples. We're going to make full circle and come back to samples shortly. So less than 150 is going to be down here, 150, right? So that's going to be equal to our Z score there is going to be equal to 150 minus 200 over 25, right? It's going to be equal to, hang on a second, that's 2 standard deviations, right? Oh, it's 20. I'm sorry, it's 20. Right? It's going to be, let's see, 50 over 20 is equal to negative 2.5. Okay, 2.5 standard deviations below the mean. Okay, so I'm going to go back to my table. If I can find it ever again, here it is. Negative 2.5, negative 2.50 represents an area of 0.0062, less than 1%, 0.0062. So, going back to my notepad. Whoops. So this, yeah, it's going to be area 150 is going to be down here actually, right? 150. Right, so this area is going to be 0.0061. Now I don't have to convert that because the question was, what's the probability that someone will be selected that's less than that value? And we're looking to the area to the left of the Z-score, so that's already what it should be, right? That's what the table always gives us, the area to the left of the Z-score. In this case, it's a negative z-score because it's on the left side of the mean. Okay, and I think we had, was there one more there? Yeah, what was that last thing? Okay, between 190 and 210. Okay, so I'm going to redraw this. Whoops. Okay, here's my distribution. Here is my mean is 200. Population mean is 200. Oops. And my standard deviation is equal to 20. And 190 and 210. Okay, pretty clear that each one of them, this is a z-score of minus 1/2, and this is a z-score of plus 1/2. Right? So I'm going to go to my table, and minus 1/2 minus 0.50 is 30.85. Right? So this area from this point south is 30.85. But what about 210 plus z-score of plus 1/2? 0.5 is 0.6915. From this point down is 0.6, what did I call it? 6915? Is that right? 6915, right? Got it. 6915, right? So what's the area between them? All I have to do is take 0.6915 and subtract 0.3085. And that'll leave me with this area in here, right? I'm taking this whole thing here, subtracting this part, and it leaves me with the section that I need, the likelihood that they would be between those two values. 5, carrier 1, 3, 8, 3.8, about 38.5, 38.5% roughly. 0.3835. Did I get that right? 383. I'm sorry, you're right. 3830. Okay. You guys got that? Are you guys online getting that? Are you okay with that also? Okay. So this is how I would use the empirical formula, or I would use the z-table to figure out the percentage of a population, given that I know it's mean and I know it's standard deviation. Figure out how a percentage, how a population is distributed, how I can predict that the likelihood of my getting a person with a certain blood pressure or a cholesterol level and so on and so forth in a population might be, given I know those things. Okay, so now we're going to move on a little bit. We're going to take a look at what happens when we start to take some samples. Okay, let me bring this back up here. Okay, now we're going to take that same population that we just spoke about, right? And we're going to take a sample size of 25 from that population. We're going to determine what's the probability that the mean of that sample is larger than 204. Well, when we were dealing with the sample population, we were asking what's the probability that a random individual that you would choose out of that population is has a value greater than 204. Now we're taking a sample size of 25. We want to know what's the likelihood that the mean of those 25 people is greater than 204. So now we're going to go back here. Where'd it go? I'm going to go back here. I'll start a new page. I'm going to go back here. And this is my original population. It might be something like this. Except now I'm dealing with my sample distribution of size 25. So it's going to be narrower. I'm not going to draw it narrower. I'm so I can get this to go away. I don't know why the undo doesn't work here. But, okay. So I'm going to draw it wide, but it's actually going to be a narrower standard deviation. So this is my distribution of all the possible sample average outcomes for sample size equal 25. So what's the spread of this? What's the standard deviation of this? Well, in fact, we don't call it standard deviation. We call it standard error. Okay, and what's that equal to? It's equal to the population standard deviation divided by the square root of the sample size. Right? So what was the population standard deviation? It was 20. Divided by the square root of sample size, 25, square root of 25 is 5. So our standard error, our standard distribution for the sample means, if we repeatedly do it over and over again, is 4, not 20, right? Not as broad. So the mean, though, we would expect is still 200, right? We would expect half the time we get a sample from a population of people that has an average cholesterol of 200, we would expect half the time we'd get a sample mean under 200, other half the time we get a sample mean over 200. So it's going to be normally distributed around the same mean. So the mean is going to stay the same. It's just going to be the standard deviation that's going to change. So I'm going to say 204, right? 204. So that's a lot narrower than before. Remember when we were looking at 204, that was pretty close to the mean. Now we're going to look at this, and we're going to do the same thing. We're going to say, okay, the z-score for this value 204 minus 200 over the standard error is equal to 4 over 4 is equal to 1. So that's going to be what's the probability of getting, what's the probability that the mean sample is larger than that, right? Well, I'm going to use the empirical formula here to save myself a little bit of time.
You did 204 minus 68.
I did 204 minus 200
Divided by 1.
divided by 4, the standard error, right? The standard distribution for the sample means is 4. This population standard deviation was 20. The standard deviation for the repeated sample means is only 4. It's a lot narrower.
What's the answer?
Okay. Well, let's see. Well, we want the one that's above, right? We're asking what's the probability of getting a sample mean that's over 204? Is that what we asked? Well, let's see. Well, one below and one above, this would be 68%, right? So from the mean to the right would be 32%. So that would leave about 34%, right? 34%, right? So that would leave 16% above. Okay.
So hold on. So the z-score was 1.
Yep.
Okay. So
Z-score is 1, right?
Where do you see
Positive 1, right? Okay, so, but we know that between one standard deviation above the mean and one below the mean represents 68% of the outcomes, right? So since this is symmetrical, that's one of the properties of normal distribution. Is it symmetrical? That means that between the mean and one standard deviation below is 34% of the population or the samples. 68%, 34, right? And 34% above, right? Adds up to 68, right? Am I right?
So it's not 68% that are in the middle. Oh, right. Sorry.
Yeah, it's 68% in the middle.
Calculating 50 minus 34.
I'm sorry.
Now you're doing 50 minus 34.
Oh, because we're interested in the percentage of outcomes for sample means that's above 204. So I want this area here that's above one standard deviation above. So I know from the mean up is 50% of the distribution, right? So if 34% is here, that leaves 16% can be in here. Okay? All right. So next. Okay, you guys online okay with that? See, I just did it without a z-table. It's not as precise, but as a matter of fact, let's do it in a z-table. See what happens if I do it in a z-table. One standard deviation. Okay, one standard deviation above represents an area of 84.13, right? 0.8413. So that would mean from this point down, from one standard deviation plus one standard deviation down, is 84.13%. And it would be, right, actually it would turn out to be 15.87%, right? Pretty close. Pretty close. Yeah, we used to have an expression, good enough for government work, right? Okay, so now, not always good enough for government work. Sometimes we want to be more precise. Okay, and I'm now going to tell you why we've been lying to you for the last 2 sessions. Okay, remember we did this whole thing with the empirical formula, and we said 95% of the population of the outcomes and so on and so forth is between 2 standard deviations below and 2 standard deviations above the mean. Well, in order for that to work, what that would mean is that 2 standard deviations for 95% of the population here, that would mean that since it's symmetrical, you would have to have exactly 2.5% of the population here and exactly 2.5% here. So let's go to our z-table and see if the z-score is really 2 here and here, minus 2 and 2 here and here, right? So we need this area to be 2.5%, 0.025, right? 0.025. Okay, so let's go to our z-table. Okay, z-table. And now this is the area, for the first one, we're going to use this one because we're interested in the area below negative to the left side, or negative z-score. So negative z-score of 2.0 represents not 2.5%, but 0.0228. So what z-score represents exactly 2.5%? Well, it looks like I'm going to have to go back up here and go across. Oh, 2.5. Oh, look at it. There it is right there. That's an area of 2.5%. And what is that number? That number is 1.96, right? So really, 1.96 represents the value where 95% of the values are between it. How about on the upper end? We'd want 97.5. Let's see. Okay, 97.5. Where is that? Positive 1.96. What a surprise. Great, right? Okay, so that number is really 1.96. Well, what do you think? There's another dirty little secret lurking here, right? What's one standard deviation below and above the mean, right? For that 68%, we actually use for one standard. I'm sorry, not for that, but very frequently we're interested in the middle 95% of the values, right? We're interested in that. We're also very frequently interested in the middle 90% of the values. For middle 90% of the values, if you look at the table carefully and go to 1.64 below and 1.64 above, that'll give you 10% on 5% on the left side, 5% on the right side, and that'll give you the middle 95%. That value is 1.64. Well, how about the middle 99%? Well, that's going to be a bigger z-score than either one of those. It's going to be 2.58 and 2.58. In fact, just to show you quickly, 2.5012345678, right? That represents 0.5%. 0.5% on the bottom, 0.5% on the top represents 1%. That means the middle 99% are between those two z-scores. Why is that important? We're going to find out in just a little while why that's important. By the time you're done with this course, they're going to be burned into your memory, right? Yeah, it's like they're tattooed. They're going to think you're tattooed with these numbers. 1.96, 1.64, and 2.58. Yeah, write them down. But by the time we're done, you won't have to write them down ever. What's that? Yeah, I think it might help for you to write it down for the first exam. Sure. Well, I'll tell you what. Let's actually put them to work. That's kind of like a recap anyway. Okay, so let's take a look. Okay, how you guys, 1.9? Oh, good. You guys online are keeping up. Good. Excellent. Okay, so now I'm going to go back here. And I'm going to go back here to this thing. What's the probability that the mean samples between we took repeated samples, empirical rule? I'm going to move on to this over here. I'm going to skip a little forward here. And we're going to use this to understand how well we really know the mean of a population from a sample that we've taken, right? So we're about to actually apply this information that we've just played around with. Okay, I could do some more samples over here with the standard error, but you get the idea. Instead of using standard deviation, I'm using standard error when I'm looking at repeated samples, okay, rather than population distributions. Okay, so now instead I'm going to take a look at this.
The 1.96
is the, no, for both. In other words, 1.96 represents the middle 95% of the values for a population or for a distribution of sample means, right? It's still got, both of them are z-scores, right? Number of standard deviations apart. So they apply to any normal distribution. It's just that right now I'm alerting you to the fact that it isn't really two. The two is that empirical rule, that's an estimate. But the real number is 1.96. Yep. Right. And we could give you another number for 3 standard deviations, but nobody ever really uses that.
And that was
Yeah, and 1 standard deviation, nobody ever really uses that. It's really the 95%, 95%, and 99% people are interested in. And pretty soon you're going to realize why we're interested in those rather than precisely 1 standard deviation, precisely 2 standards, precisely 3. 95%, middle 95%. 1.64 is the middle 90%. And of course, 2.58 is the middle 99%. It's the widest. That's why the z-scores are so far apart from each other. Right? It encompasses more. 99%. Okay, so I'm going to go over here to exercise 6. The first one that really involves confidence intervals. I just want to jump into confidence intervals so you get a look at it. Then we'll go through the lecture, which will go over a lot of this material again in a different format. And then we'll come back after the lecture and we'll try and cement this in. Okay, so we're going to get 3 shots at this thing. Right? So repetition is good when, there's confusing stuff like this. Okay, so the weight of adult males 18 to 65 is approximately normally distributed with a standard deviation of 30 pounds. I'm giving you the standard deviation of the population. Generally, you don't know what it is, but for this case, I'm giving it to you. There's a reason why I'm giving it to you, because the spread of I don't want to, at this point, introduce too much variability. In other words, if I were to just give you a sample of, what's the sample size here? 25 people, and told you the mean of those 25 people that we sampled, and the standard deviation of the sample, well, then you'd have 2 pieces of uncertainty. You'd have the mean is uncertain, and the standard deviation is uncertain because you don't know what the population standard deviation really is. So for now, for today, I'm giving you the population standard deviation. And for all the rest of today, we're going to work that way. Okay, so the weight of adult males is 1865, has a standard deviation of 30 pounds, population standard deviation. You randomly sample 25 men for that population and find a sample mean of 150 pounds. Okay, let's take a look at what we got here. 150 pounds, standard deviation of 30, sample size 25. Okay, let's see. Sample mean is 150. The standard deviation for the population is equal to 30, and our sample size is equal to 25. Okay, so if I assume for a moment that I got lucky and that's what the population mean really is, I would expect that if I took repeated samples over and over and over again, that I would get samples with a mean of 150.
One question. So
Yeah.
X means that this is a mean.
That's
of
a
sample.
mean of a sample, right? When you see mu,
Standard deviation of the sample should be
sigma.
sigma.
No. Standard deviation of a sample is SD.
SD, right?
Yep,
so
SD.
Sigma is for the population.
What's that?
Sigma is for population.
Correct. I'm giving you the population standard deviation. So SD for these samples, for all of these samples, right? Okay. In fact, really, I'm going to call it standard error, right? Is 30 divided by the square root of 25, right? Sigma over the square root of the sample size, right? That's equal to 30 divided by 5 is equal to 6, right? So I got a mean of 150. So I can say to myself, I would expect that the variability in the population is 30, the standard deviation is 30, but the variability for the sample means is 6. So if I got lucky and the mean is truly 150, then I would expect 95% of the time my sample means are going to be between are going to be 150, right? Plus or minus, right? If I go to the left, it's going to be minus the standard error, 1.96. I'm not going to use 2 this time. I'm going to use 1.96 times the standard deviation, or in this case, the standard error, right? So, okay, 150 plus or minus 1.96 times 6, right? Okay, so good. Let me think about this. Okay, so that's 150 minus, I'm going to round this to 2 just for the moment, minus 12 on one side and 150 plus 12 on the other side, or in other words, 148 to 162, right? Well, I really don't know if the mean really is between these two numbers. Why don't I know that? Because I don't know how, this might have been the one time out of 20 that I was outside of the 95% likelihood of getting within 2 standard deviation of the population. So I really don't know any more than I really knew before, except that I know with 95% certainty, right? Because I know the standard deviation and the standard error. I know with 95% certainty that the true population mean, mu, 1/5 mu, is between 148 and 162. How do I know that? Because I know that I wouldn't expect that to get a sample that was that extreme. That, in other words, 150 might have been at this end, and the true population mean might have been 168 or 162, right? Or it could have been 150 is at this end. We're 95% sure 150, instead of being in the middle, could have been at this end, and the true mean could have been at 148, right? I know that there's 95% likelihood that the true mean is going to be within 2 standard deviations, 1.96 standard deviations, below that 150 or above that 150. So even though I don't know the true population mean, mu, even though I don't know that, I know that there's a range within which I can be 95% certain that I've captured it. Now, what's going to happen 5% of the time? I'm going to be wrong. That's the nature of statistics, right? This is not physics. You know, with physics, you take a rock, you hold it here, you drop it, you know exactly what it's going to do. In nature, we have a lot of uncertainty, a lot of variability. So we're never 100% sure. But what's that? 138? Yeah, 138. Right. So in nature, when we're dealing with distributions like this, we're never 100% sure. But think about the power this gives you now. Now, even though you don't know what mu is for sure, you have a range within which you can be 95% sure that it's likely in that range. Okay, well, why is that useful? Well, that might be useful for, among other things, you know, let's say I take a sample of Americans and I find their serum cholesterol is 200 for average American. I take a sample of 25 Americans and the average serum cholesterol for those 25 Americans is 200, right? Now, let's say I go to France, I take a sample of 25 Frenchmen, and their average cholesterol is 180. Well, gee, this isn't the population mean. This isn't the population mean for Frenchmen, right? It looks to me like Americans have a higher cholesterol than Frenchmen, but I don't know if the difference is due to chance or if the difference is real, if the difference is significant. I can't really tell because I don't know what the true population mean is. Now, if I look at this not from the perspective of what I calculated as the mean, but as my confidence interval, well, let's say my confidence interval for Americans was 190 to 210. I'm 95% sure, right, that my true population mean for Americans is 190 to 210. And with the Frenchmen, let's say my 95% confidence interval is 175 to 185. My 95% confidence. Maybe the numbers are tighter there. Confidence interval, right? So what can you tell me about here? They don't overlap, do they? So in a sense, you can say I'm 95% sure that American men have an average serum cholesterol of between these two numbers. I'm 95% sure that Frenchmen have a serum cholesterol between these two numbers. That means I'm 95% sure that the mean cholesterol for Americans does not equal the mean cholesterol for Frenchmen. That there's a difference. I made them up. Okay, I made them up. They'll be based on the sample size, the standard deviation for the population, and so on and so forth. But you see, the deal here is now when I only knew the means, there was no way for me to tell what the likelihood of me being wrong or right if I only knew the mean. But now, by using a confidence interval instead of the mean, I can quantify my level of certainty or uncertainty, my confidence. So we're going to be using confidence intervals like this. So the key to using a confidence interval is a range within which you have a level of certainty about what the population mean is. Okay. Sometimes you want a confidence interval which is very high, like 99% confidence interval. Most of the time, you're going to want a 95% confidence interval. Sometimes you might be satisfied with a lower level of confidence, 90%. Okay, which of these things? Okay, let's say that the 95% confidence interval is 180 to 220, right? Would you expect the 99% confidence interval to be wider or narrower? Narrower. Okay, you're wrong. Think about this for a second. You want to be more certain that you actually capture the mean. You make it wider, you give yourself a bigger target, right? So if you want to be 99% confident, you would want a confidence interval that's wider. If you're willing to be less certain, 90%, then you can make your confidence interval narrower. Okay? How does that work out mathematically? Well, in this case, let's say I'm working on the problem we were working on before. Let's say that the weight is 150 plus or minus, well, in order to calculate confidence interval for 95% confidence interval, I said 1.96, right, two standard deviations, times the standard error. Standard error is always going to be the same based on the population standard deviation and the sample size, right? So now, what if I want to make, that's for a 95% confidence interval. If I want to make it a 99% confidence interval, what do I change about this formula? Exactly, you change that z-score. 150 plus or minus 2.58 times the standard error, right? So now it's a wider range. What do you think we call this part over here? 1.96 times the standard error, 2.58 times the standard error. What do you think a good name for that would be? How about margin of error? That's what we call the margin of error, right? That's part of our confidence interval. This can be a little confusing first time out, but as we go through exercises with this, it's going to become clearer and clearer. And just to finish, go full circle. Just to go full circle, if I want a 90% confidence interval, I can use 1.64 times the standard error. So that makes my margin of error smaller. So the number below, the difference between the number below and the difference above are going to be a smaller range in numbers. Okay. So concept-wise, this can seem a little challenging. When we actually put it to work, if you follow a few basic rules and remember a couple of numbers like 1.96 and 2.58 and so on and so forth, it's really going to be simple to apply. But there's some basic rules you got to remember to apply, such as make sure you know that that when you're dealing with samples and when you're dealing with population parameters. In other words, if a problem tells you that the population standard deviation is such, then sample size is such, you got to remember you have to convert to standard error to calculate your. You got to calculate your standard error, standard deviation for sample means. in order to calculate your confidence interval.
The only way in which we don't have to convert standard error is everything is given to us for the calculation.
Right. Yeah. So the reason why we went through all of this is because our justification for being able to do this and create a confidence interval is all based on what happens when we take repeated samples from a population, how the results in all those sample means generates a new distribution and what the properties of that new distribution are. Now we know that the main difference between the population distribution and the sample distribution is that the spread is different. The spread is narrower for the sample distribution. And the relationship of the two spreads, the two standard deviations, is for the population, you have sigma, and then for the mean, all the means, the distribution of all the means, the new standard deviation is called the standard error, and it's calculated by taking the population standard deviation and dividing it by the square root of the sample size. That gives you a window onto how much narrower it is than the population. Okay, so let's take a 5-minute break. We'll come back. We'll see the videos. You guys online, take a look at the video. Everybody. When I make a mistake, everybody is critical now. Thank you very much. We know it's 1:38. Okay, so let's take a break. You guys online, watch the videos. It's 6:32 now. Let's come back at about 7:30, and we will have watched those videos here, and we'll kind of post-mortem this and go over a few examples. Okay, and there's a link. If you go back to session five, the folder, use that link for rejoining us here. Okay, see you guys in a little while.